A capacitor is a device that stores energy in an electric field formed between two conductors with equal magnitude but opposite charge, positive or negative. When there is potential difference across the conductors, an electric field develops across the dielectric, causing positive charge to collect on one plate and negative charge on the other plate. When two parallel plates are connected across the battery, the plates become charged. An electric field will be established between them. The figure on the right shows capacitance of a parallel plate capacitor. Using the definition of capacitance, we can determine the capacitance C of an ideal capacitor as a function of its structure. This equation for the capacitance of a parallel capacitor shows that C is a constant independent of the charge stored on the plates or the voltage across the capacitor. The amount of charge needed to produce a potential difference in the capacitor depends on area of the plates, distance between the plates, and non-conducting material between the plate. The image on the right shows the formula of capacitance. Objectives. First, to verify the dependence of capacitor on plate size and spacing for a parallel plate capacitor. Second, to measure the capacitance of the capacitor.
Procedure consists of two parts. Part A, to verify the dependence of capacitance on plate size for parallel plate capacitor. Part B, to verify the dependence of capacitance on spacing between the plate for parallel plate capacitor. Part A, first, using field interactive simulation, use capacitor lab basis to do the experiment. Second, the separation between plates are kept constant and recorded. Third, the first plate area 100 mm squared are recorded. Fourth, record the capacitance that is observed. Fifth, calculate the dielectric constant K using the measured value. Sixth, repeat the step 3 for 5 different measurements. 7. Plot the graph of capacitance picofarad versus area millimeter squared. Part B. First, use the same simulator. Second, the area is kept constant and recorded. Third, the first separation between plate 2 mm are recorded. Fourth, the capacitance are recorded. Fifth, calculate dielectric constant K using the measured value. Sixth, plot the graph of capacitance picofarad versus the plate separation millimeter.
For discussion, from part A we should be able to see the relation between the capacitance and the area of the plate, where the result shows such that when the area of the plate increase, while separation between plates are kept constant, the capacitance increase. And in part B, the relation between the capacitance and the separation between plates were observed, where when the separation between plates was increased, while area of the plates are kept constant, the capacitance decrease. And the dielectric constant K were also calculated using the formula as shown in the video, where dielectric constant is defined as the ratio of the electric permeability of the material to the electric permeability of free space, which is vacuum. After conducting the experiment, the conclusion we came up is that the objective of the experiment are successfully achieved, and the result are able to verify the theory which states that when the area of the plate is increased, capacitance will also increase, showing the area of the plate is directly proportional to capacitance, while when the separation of the plate is increased, capacitance will decrease, showing an inversely proportional relation. This shows that capacitance of parallel plate capacitor are dependent to the area of parallel plate and separation size between two parallel plates.